Okay, this is now the second video on electric fields. These are just some representations here of electric fields. We've got a point charge in this particular case and two charges here that are like charges. We can't tell by looking at these diagrams whether they're positive or negative, but I think we've discussed, or we were discussing this in class anyway. Nothing that you need to write down from that one, apart from perhaps the heading electric field lines. All right, so what are electric fields? Electric fields then are a force field, and we use electric field lines to represent the field. Field lines do not exist as such. They are simply a representation of the nature of the force field. Okay, two things we can figure out from field lines. I'll just sketch a little diagram here, but they're more neatly drawn on the next slides. Let's say this is the electric field around a point charge. It's going to have a direction. So one thing that the field lines give us then is the direction of the field. And the other thing that they can indicate is the relative strength of the field. So in here, the field lines are reasonably close together. So the field is stronger than it is out here where the field lines are further apart. Just take note, the field does exist everywhere in between the field lines as well. It's not just where the field lines are. So when we say it represents the field, and direction of arrows gives the direction of the field. And the relative spacing of the arrows, or the spacing of the arrows, or spacing of lines, gives the relative strength of the field. Okay, so just drawing a few diagrams. This first one will make this a positive charge. So if we have a positive charge, by definition, the direction of the field lines is away or from that positive charge. If over here we have a negative charge, you can draw exactly the same diagram as this one, except this time you will change the direction of the field lines and have the field lines pointing towards the charge. Right, so by definition, field lines go away from positive charge and they go towards negative charges. So draw both of these diagrams and complete that one for a negative charge in your notes. All right, two separate diagrams here. Top one, positive charge. Let's make this a negative charge. Okay, so the shape of the field, and I'm just going to sketch this as carefully as I can, but it's freehand. We've got a field line going straight across. Basically, a positive charge placed somewhere in here would move in a straight line as indicated by that field there. Let's get rid of the lower one of those. Always tricky mucking around with these diagrams. Okay, and then we try our best to draw a diagram that looks fairly symmetrical. And the only thing I'm not so happy with is that little bit there. It doesn't quite enter the charge the way I would like it to. It's a little bit coming a little bit short. We should mark the direction from positive to negative. This time we've got two like charges. Let's make them both positive, but they could just as easily be both negative. We have an axis of symmetry down the middle, if they are equal magnitude charges anyway. And the shape of the field looks something like this. Oops, that one's a bit far over, so I don't like that. a bit more symmetrical, something like that. And again, because they're positive charges, the field lines are all going to go away. If you draw two negative charges, the diagram would have the same shape, except the field lines would be drawn going towards the charges instead. And this time we've got two parallel, what we call plates, metal plates, which we charge up in some way. So we end up, let's say, with positive charge on this plate. So that's the positive plate. We end up with negative charge on that plate. Our field lines go from positive to negative, so they'll be that way. And we have what is called a uniform field. In other words, the field is the same strength everywhere between those plates. And therefore, if you placed an electric charge anywhere, the same size charge anyway, anywhere in the field, it would experience exactly the same size force. Let's just tidy that up a little bit if I can without rubbing out the wrong bits. Close. There is a little bit of what's known as an end effect here, but generally speaking, I wouldn't bother drawing those in. I would just draw in the parallel lines. Okay, and when you draw the diagram, make sure you use a ruler. Okay, ruler. And you're looking for equally spaced parallel lines. Just make sure your diagram is well done. All right, electric field strength. By definition, electric field strength is defined as force per unit positive charge. I think if you're asked to give a definition of electric field strength, let's say in an exam question, if you wrote down force per unit charge, you'd get 1 mark. If you write down force per unit positive charge, you'll get the 2nd mark. Why positive? Simply related to the fact that we're defining electric fields as going away from positive charges. All right, so as a formula, we're saying E. E here stands for electric field, so don't mix that up, please, with energy. Think about the context of the question and what it's asking about. So electric field strength E equals F divided by Q. So if we have a look at that and just think about units from the formula, the units of electric field strength must be newtons per coulomb. Right, and just an example, problem to work on. Calculate the size of the force if a charge is placed, it's an electron placed in an electric field. So you're just going to use this F equals E times Q. Where does that come from? If we just go back previous page, E equals FQ. Very useful form of the formula then would be F equals EQ. Okay, to calculate the size of the force if you know the electric field strength. So in this particular case, you're using the E value and you're going to use the charge on the electron 1.60 by 10 to the negative 19 coulombs. And then to calculate the acceleration of the electron, once you've got the force, then acceleration equals force divided by mass, F equals ma. But you need the mass of the electron. An electron has a mass of 9.1 times 10 to the negative 31 kilograms. So you're going to use that to figure out the acceleration. And I think when you take what is a relatively, what you'll think of as being a small force in your first part of the calculation, but divide by a very, very small mass, you're going to find that you still get a pretty huge acceleration being produced by that electric field. Okay, we're going to leave this particular video here, and so I'll break it up into 3 videos, and we'll complete the topic with a 3rd video.